nomenclature terminology. The steering element retains its name from the tube. It's called gate once again. The positive element is not called cathode anymore, but the collector and the anode is called the emitter, because in physical reality electricity flows from negative to the positive pole, but in our teaching it's all the other way around. And you remember this is a very low current, and this can be a high current or powerful current, and usually here you have a resistance of about 10 kilo ohm, and this powerful electrical current usually controls or steers your workload. Workload is one of the words I simply forgot yesterday and could only produce in German. And this workload can be of a machine or lamp, a bulb on the ceiling or what else, whatever you have. But usually the workload is of a more electrical and or electronical kind. And transistors can be combined just as tubes, and because they are much smaller, many more transistors can be combined on one printed circuit or later on in still better forms. Time goes by. And nevertheless, the so-called bipolar transistor, in our instance, example case, bipolar between connected between a positive voltage and a relatively to positive negative value of 0. It's lesser than 12, therefore it's structurally a negative pole, and a positive and a negative pole are connected by this transistor, and that's why it's called a bipolar transistor. And this device has many disadvantages in relation to the tube. It's much more noisy because you laugh if you hear the astronomical reason. As I told you, nobody knows really what noise is and what makes noise in our bodies and in electronic devices. But we presuppose, we hypothesize that the causes of mini noise, let's say, of transistor noise, are alpha particles in the universe and gamma particles in the universe, and they are the only random events ever discovered for the good or bad reason that to produce randomness by computer algorithms is a contradiction in itself. All algorithmus generated random is pseudo-random. But transistors react to real random, statistical random, cosmological random, and that's why we are good random generators. We for instance, we computer musicians need transistors badly because we want to make not only music but also some amount of noise. Otherwise, the generated sounds would sound clinically clean, as in hospitals. Got the point? And we have no violins with their noise, or saxophones with their noise, but we have only algorithms to produce music, and so noise has to be introduced by some transistor, as Bob Moog, the inventor of the synthesizer, knew all too well. And it took many decades, or some decades, before the bipolar transistor was replaced by the so-called field effect transistor, or FET. All of that applies also to so-called FETs, but the resistance between gate and the two and collector and emitter is much more higher than in the other case, and so the noise is less, and all actual computer circuitry is made of field effect transistors connected together to compose flip-flops. And now you know flip-flops. And that somehow, pathetically, I could say, with field effect transistors, your little finger can control this world. Next step in miniaturization had less peaceful causes or origins than the transistor. Somebody was heavily interested in miniaturization, in still further miniaturization. Little computers built up by many transistors existed in Manchester, England, in the US, surely, but they took too much room. And somebody, you may imagine who, asked the engineers to put many transistors on the same physical silicon die. And this succeeded and was called integrated circuits. Transistors, very small transistors, very small or invisible to human eyes, very small resistors and tiny capacitors were integrated, united on one physical, chemical base of some millimeter power 2. And many of these integrated circuits, ICs, let's call them by their technical name, could be combined to a small working computer, and this working computer had little weight and little volume and could be put where? Remember the V2 dear to Peenemünde in Thomas Pynchon? Imagine?
On a bomb.
Hmm?
On a bomb? No.
No. You are too far away.
Oh.
Inside?
Plane.
Hmm?
Plane.
No. You are too far from Peenemünde with your answers.
Where it could be put inside?
Yeah?
Radio.
No.
Radar?
You're still too far away from the very elementary answer, my dear Watson. Yeah. Intercontinental rocket called Minuteman. The small man, the small rocket. The rocket wasn't small at all. The rocket was huge, but its computer system, onboard computer system, was so miniaturized, so mini, that the rocket could be called Minuteman by the Pentagon or by the engineers of Cape Canaveral, later Cape Kennedy. Time goes by? No. It's okay. But we have to make a break in 10 minutes. I forgot almost in my enthusiasm on chip technology. Let's, for a moment, we leave this issue of ICs, of integrated circuits. Before coming to the computer as a hardware and software device, before describing this device, I'd like to make my final adieu to the analog circuitry and to express my final respect to it. Nowadays, people tend to forget the historical fact that not only digital circuitry but also analog circuitry could and can be still integrated on a large scale by integrated circuits. And the most brilliant and most universal device of contemporary analog circuitry is the so-called operational amplifier, also called op-amp, like sys-op in the case of system operator. And an op-amp is a dream of musical processing, for instance. And replaces historically all transistor filters and oscillators and amplifiers and can integrate them in just one circuit chip. And so we don't know the inside of this integrated op-amp. We just have its symbol. it's connected somehow between positive voltage and Mars, Earth, Mother Earth, and has two inputs and one output. And one of these two inputs amplifies the signal, the incoming signal in a positive sense. Polarities are kept but amplified. Whereas in the other case, as you can already imagine, the incoming signal is inverted, negated before amplifying it. And once again, you are this workload, and once again you are invited to ask why two inputs instead of just one positive input, because amplifying means increasing. Why should we invert or decrease the value? Decrement, sorry, the value. Answer, as I gave it in the yesterday in introducing you into feedback theory. You take a very small part of the output and feed this very small part on the negative input, the amplification becomes much more linear and without distortions. That is why op-amps without feedback loops, this is a resistor, you may remember, would amplify times, let's say, 1 million. This is, which makes absolutely no sense, because given the 15 volt voltage range of the amplification. So the amplification has to be decreased and decreased extremely or heavily, down from, let's say, 1 million to 10 or 100. But this loss of amplification gain is compensated by the gain in linearity, and that is in precision. The output signal structurally follows precisely the input signal, and there's no op-amp produced noise and so on. Okay, and you can do so many things with op-amps, but I have to go on. And so, just the final. There you see how fast we are in drawing pictures and diagrams. And one wonderful application of op-amps and analog oscillator devices has been invented by Robert Moog, whom I had the chance and honor to speak for one evening in Austria. And young Bob Moog was just an engineer in some hardware engineering company, small company in upstate New York. And his colleagues constructed one voltage oscillator, voltage controlled oscillator after the other. And these engineering tools were applied then for the debugging, we would say today, of existing wireless stations, about their qualities of signals, and so on and so on and so on and so on. And that's why Moog's colleagues produced linear oscillators, that is, if your input had a value of 1, then the oscillator produced a frequency of, let's say, 50 cycles per second, 50 hertz. If you double this 1 input volt to 2 input volt, it would produce 100 hertz. If you made it 3 volts, the input, it would give you 150 hertz, and so on and so on. And for testing radio equipment, this oscillator was perfect. But Moog said to his colleagues, I want to make music with your oscillator. I want to buy and construct my first synthesizer in this world. And I'm sorry, I can't do with your linear oscillator sine wave producer, in fact, rectangle wave producer. Okay. I need an exponential voltage line. Not this way, what? This would be linearity, y equals z, and this would be the function e power x. And the colleagues asked at Moog, why should we build you an oscillator with exponential characteristics? And Moog's answer was, because music is Pythagorean. And my oscillator should proceed as follows. Input of 1 octave, as in the former example, should again give 50 hertz, and 2 volts should give again 100 hertz, but I'm sorry. Yes, but I shouldn't. It's time to make a break, and let's say the sequence of higher and higher and higher octaves is a power n, and music is built up is constructed by way of putting octaves one above the next, the lower one. And my numerics example I have to control once again during a break. See you. putting new power into me. This orange juice brings me in mind that I forgot to answer one of the terminology questions raised by the transistor. I explained you collector, emitter and gate. I didn't explain its very name and the reason of this artificial word coining transistor. You may guess the reason and the etymological origin. Transistor stems from resistor, obviously, and tries to suggest verbally the fact that a transistor is sometimes that a transistor behaves like a transistor, but it behaves as a transistor whose resistance can be controlled by voltage, in difference to a usual resistor. And this voltage controlled resistance is obviously an analog principle. Transistors can get into any state between off and on. They can become off, they can become on, but they can also take the value of half open. Yeah? So let's take the metaphor of a door which is half open, meaning that you can't pass through this door, but your child can. So this small example is made up by me in order to show you that transistors are, by their nature, analog devices. And in order to, in order to arrive at the digital behavior of transistors, and in the case of flip-flops and all this stuff, the transistor is used as only as producing its two extreme outputs, its maximum and its minimum. Of course, in physical reality, this ideal behavior can never be reached. It would look like this, but there is no, in nature there is no timeless step in 0 seconds from low to high. So, if you look at this signal in its physical reality on Ferdinand Braun's oscillograph or oscilloscope, you will see this rather blue picture or diagram, anechoic. But for a computer system, physical reality doesn't matter. And not only for the software, but for the hardware which is somehow idealized. But this is the first idealization that really works in opposition to Plato's ideas. To give you a very elementary instantiation of this, of a generator which is able to produce this output. I take a simple op-amp, operational amplifier, and reduce its input symbolically or practically just to the negative input. But there is no input at all. In fact, the output comes back to the input, which I would call, and you would now call a feedback loop. Considered with the eyes of a logical philosopher, this thing is impossible, cannot exist at all. It's a living paradox. It's a running paradox. Because in the binary case, the input would be O and the output would be thus 1, and they can't, these on one and the same wire, 1 and 0 can't coexist. It's a short circuit. But in physical reality, no problem. Every wire is somehow also a resistor and in some way also a capacitor, and so you need neither physical resistor nor physical capacitor. The wire itself suffices to produce a living paradox and a possible paradox, and this would be precisely this output. And in very primitive computer systems in the early days, this operational amplifier was really, factually, the master clock. You must imagine, without any resistor and without any capacitor, this inverter, this not element, this negator, produces a digital frequency at its maximum. It runs as fast as possible. It can't otherwise do. And so, and the master clock in computer systems is precisely this artificial micro time which controls and synchronizes every logical binary digital step of the whole system. The master clock is connected to every important chip on the board, on the motherboard, because all chips have to be synchronized in order to collaborate. Nowadays it's a quartz chip, because quartz is oscillating much more precisely than my old-fashioned op-amp. And then the master clock actually would be at heights of 3 or 4 gigahertz. in order now to come from elementary machines to actual computer devices, a very short historical excursion. Anticipating, unfortunately, on the difference between CPU and RAM. Hopefully you know that, or keep in mind that CPU means Central Processing Unit, the old arithmetical logical control, and RAM means random access memory in difference to ROM, read-only memory. Random access memory should better be called read and write memory in the sense of Turing's ribbon, read-only versus read and write chips, memory chips. And at a given historical time during the Cold War, Asia, Far East, in European eyes, surpassed the US hardware industry in producing very complex RAMs and other secondary chip devices. And the Pentagon accepted this situation, and actually, and still today, RAMs are produced just as monitors and so on in Japan, in Korea, in Taiwan. But the Pentagon was very interested that the world leadership, the world lead in CPU engineering and design remained inside the USA and accessible to the National Security Agency, the leading computer company or administration company of the world. And so Pentagon and NSA almost forced the hardware, the chip industry to the next integration step called VLSI, Very Large Scale Integration. And at the moment, Intel has been surpassed by NVIDIA Corporation in integration, in very large scale integration capacity. The NVIDIA graphical GPUs graphic processing units there are about, I think, 3 billion of transistors on one and the same chip, and Intel's CPUs linger between 1.5 billion and 2 billion transistors on chip. More to this topic tomorrow.
Who is that company? Is that AMD?
NVIDIA?
Oh, NVIDIA, yeah.
I didn't pronounce it correctly? No.
I didn't hear it.
Hmm?
I just didn't hear it.
I'm sorry, but I call it NVIDIA, being a German. And it's my politeness to you that I talk of billions where I would say Milliarden in German. And in Germany this makes more sense than to jump from millions to billions, meaning 100 million. So, this was an historical interplay that commercial war continues on the conditions of peaceful land conditions. Taiwan, Southern Korea, and Japan and the US, as you know, are still in the same boat. Back to structural, to talk about structures. I wonder whether I should invert the presentation order or not, but you are very polite and patient, and so I continue as I devised it at home. Everybody of you know this threefold differentiation between hardware, software, and so-called wetware. Wetware, obviously, I'm not sure, means ourselves, very wet beings made mostly out of water. Soft targets in military slang, because it's difficult to kill. Soft targets. Software, as you know, is made up of alphanumeric code. That is the code whose signs, symbols, combine the 26 alphabetic signs and the 10 decadic signs, and some punctuation marks are allowed in software, some not. The only punctuation signs allowed are US American signs. It's the ASCII code, and European signs, as a Spanish question mark, also are not allowed in software coding, and it's okay so, because the formal language should be beyond national differences, and historical facts don't matter in writing systems. Think of my little discussion of the Greek vocalic alphabet, which we all took over. So we programmers took over the American 127 allowed symbols, and only end users get their Chinese signs and symbols and Thai symbols and European exceptional signs and everything they want. We programmers, in order to be understandable worldwide, we restrain our source code for software, for running software, to these American signs. And you know, hardware as my main topic in these 3 days, from scratch, I hope to say. And you know the general, you may guess the general rule that what former was done by wetware it's better to implement it in software or by software. Human calculation is slower than computer calculation, but more inventive, let me say. And if and when software runs too slow for practical purposes, may they be commercial or military or crypto analytical or graphical, it's better to switch from software to hardware, and this has been done in the last decades, to my astonishment, especially in computer graphics, and as I please myself to regard me as some time member of the computer graphics community, having written a Radiosity program and a Ray Tracer, and some other programs. One of you proposed to show my Mandelbrot coding probably tomorrow on the Beamer. And it struck me that everything we formerly coded in software as vector graphics and so on nowadays goes into hardware, NVIDIA graphic chips, engines, or AMD graphic chips, and they become better and better, but still not. Nowadays they are okay to render high quality TV on the computer monitor for scientific people. They are still too slow and seen under the regard of, how should I say, they are still slow compared to the sun. In microseconds, the sun changes this very room into a color wonder, and computer hardware, graphics hardware, has some difficult time to equal the sun in producing bleeding of colors and shadows and indirect shadows and shadows of shadows and reflections of reflections of reflections and refractions of refractions of refraction and anisotropic reflection, and that is to say the mirroring of the fur of a cat. Yeah? It has been done, but only very recently. So Baudelaire's problems are still unsolved, only partially solved. Okay. After this rather poetic introduction into software and hardware, let me first turn to computer hardware and then to software. This is a logical order. We, as you'll hear tomorrow, I'm against the top-down approach. I'm pleading for the bottom-up approach for good philosophical reasons and biological reasons. And I start with the confession that, or the precision that the colossi in Bletchley Park were dedicated computers, not general computers. The first general computer, to my knowledge, was begun by by some engineers whose names I've forgotten, but then I think the first or the second American General Computer was shortly before it was finished, taken over by the great genius of John von Neumann, to the shock of the engineers who hoped to get immortality, but this immortality remained on Neumann's first draft on this Edward computer, where John von Neumann gave definitions of the von Neumann hardware architecture or system. And in this system, in this hardware system, I'll come to this architecture in some minutes. First, let me say that von Neumann took over not only the second, but also the first computer, the famous ENIAC. An acronym I'm unable to analyze. It doesn't matter. Which was a machine with, just like a Moog synthesizer, you had many little cables with my English. Stecker. Plugs, yeah. Little 1 meter cables with 2 plugs, and the ENIAC had many holes, many holes. The ENIAC filled a room of this size, and so the programming people, humans, wandered around and plugged in and plugged out for the given actual computation. And these plug-in people were directed by Claire von Neumann, Johnny's wife, and these operators or computers in the human sense all were female. So the programming started on the female side of the world. And in American eyes, even compiling as the logical continuation of plugging and plugging in, plugging out, started with Vice Admiral Grace Hopper of the US Navy. But here in Switzerland, I have to confess that the famous engineer of the Eidgenössische Technische Hochschule, Swiss Technical High School, Zurich, anticipated her slightly. So this man was an exception in this all-female programming field. This plugging in, plugging out took days to execute. The next step to produce human computer input by human computer input was called batch operation. One central computer, for example, based inside the MIT, was connected to many keyboards, just typewriters with some extensions, in the home of engineering students, and they could type in, give in on this keyboard their programming code, and it was transmitted to the main central computer, and in batch mode all these programs were executed and the result was given back to the individual programmer and student. And because all these demands on computing time had to be ordered, the machine's power was given first to this student, and to this, and then to that, and so on. Now, next step was, I skipped my first step, Intel operation. I started with, as I said, to give by 500 in 500 steps, 500 times 8 steps, I produced some opcode sequence and put it onto my printed circuit in Intel opcode. And Intel opcode is just alphanumeric, it's just hexadecimal code and unreadable to other humans. And then Intel and Motorola and other companies were nice enough to turn opcode, where, for instance, multiply was represented by the number 17 and division by the number 18 and so on, was replaced by mult and diff and add and sub and add as an abbreviation of add or and mult as an abbreviation of multiply, and diff as an abbreviation of divide. Now as a command, as an instruction. Germans say command, probably because of their history, and Americans say instruction. But it depends. Some American manuals also speak about commands. And the Pentagon goes on to use this word. And so I heard about assembler in the late 60s, my God. And in the late 70s, I wrote Intel assembler, and in the 80s, I bought an Intel 386 machine. Okay, and continue to write Intel assembler code. And I have to remind myself and you